Hello everyone. So today I'm gonna try and solve a sample problem for the Brayton cycle. So here it is. In a gas turbine unit, air enters the combustion chamber at 550 kPa at 227 degrees Celsius and 43 meters per second. The products of combustion leave the combustor at 511 kPa and 1004 degrees Celsius and 140 meters per second. Liquid fuel enters with a heating value of 43,000 kilojoules per kilogram for fuel-air ratio of 0.0229. What is the combustor efficiency of the unit in percent? So the solution is we have the heat supplied by the fuel, which is the mass of the fuel, times the heat added by the fuel. Excuse me. So 0.0299229 times the heat added by the fuel, which is 43,000, and then we can calculate with for the answer of 984.7 kilojoules per kilogram of air. So for the heat absorbed, we have the Cp of air, which is 1.0 times the temperature difference, which is 1004 minus the initial temperature, which is 227, plus the 1/2 times the quantity of the volume 2 squared minus the volume of at point 1 squared. So we have 140, and then 140 squared minus 43 squared divided by 1000 to convert. So we have 785.9 kilojoules per kilogram of air. So for the combustor efficiency, we just divide 785.9 divided by the heat supplied by the fuel, which is 984.7, which is 79.8% combustor efficiency. So next sample problem, air enters the compressor of a gas turbine at 100 kPa and 300 degrees Kelvin with a volume flow rate of 5 meters cubic per second. The volume of pressure ratio is 10, and its isentropic efficiency is 85%. At the inlet to the turbine, the pressure is 950 kPa, and the temperature is 1400 Kelvin. The turbine has an isentropic efficiency of 88%, and the exit pressure is 100%, 100 kPa. Based on an air standard analysis, what is the thermal efficiency of the cycle in percent? So air standard analysis, we can use 1.4 and CP of 1.0. So here's the solution. So first we solve for the mass flow rate. So we already have the pressure, the volume, flow rate, and then the required mass flow rate, and then since air is standard, we can use 0.287 kilojoules per kilogram Kelvin times the temperature, which is 300 degrees Celsius. So we can find the mass, which is 5.81 kilograms per second. So we can solve now for T2. Solve for T2. So T2 over T1 is equals to the pressure difference, which is already given. And then we have the K, which is 1.4 minus 1, then 1.4. Then the T2, the temperature at point 2 is 579 degrees Kelvin. So solving for T4, we have T3, which is already given, divided by T4 is equals to P3, which is 950, and then 1000 for P4 raised to 1.4 minus 1 divided by 1.4. We have T4 of 736 Kelvin. So solving for the work in the compressor work. So we have MCP delta T, which is 5.81. We solve for the mass flow rate. Then the CP of 1.0 times the temperature at point 2, which is 579, minus the temperature at point 1, which is 300. So we have 1,621 kilojoules per second. So solving for the ideal compressor work, so compressor work divided by the compressor efficiency. So we have 16 to 1 divided by 0.85, which is the compressor efficiency, which is equals to 1,907 kilowatts. So we also solve for the turbine work. So we have MCP T3 minus T4, which is equals to 5.81 the mass times the CP of air, which is 1.0, times the temperature at point 3, which is 1,400. We just solved it. So and then the T3 and then T4. So we substitute and then we solve. I'm sorry, the T3 is 1,400 and then the T4 is 736. So we just calculate it and then we can get the 3858 kilowatts. So for the turbine work, we just multiply the work of the turbine times the efficiency, the turbine efficiency. So we have 3858 times 0.88, which is equals to 3395 kilowatts. So now we can solve for the ideal work of the system. So we have 3395 minus the work of the ideal work of the turbine minus the ideal work of the compressor, which is 3395 minus 1907, which is equals to 1488 kilowatts. So solving for the heat added, and then MCP T3 minus T2, so the heat added would be 5.81 the mass times 1.0 times 1,400, which is the from point 3 to point 2, the temperature difference, minus 579. So we have 4,770 kilowatts. So for solving for the cycle efficiency, we just divide the ideal total work of the system divided by the heat added, which is 1488 divided by the heat added 4770. So we have an efficiency of 31.19%. So that's it. Thank you for watching.